So, good morning, friends. Myself Chandu Potangale. Today we are going to learn about the molecular interpretation of equilibrium constant. So, our topic of today's discussion is the molecular interpretation of equilibrium constant. Molecular interpretation of equilibrium constant. Now, so equilibrium constant, when we learned the physical significance of the equilibrium constant, the equilibrium constant is the only term when the equilibrium is attained that determines the composition of the reaction mixture, uh, that is the reactant as well as product. How much reactant is there and how much product is there, that determines the equilibrium constant, and that is only the function of temperature, right? One can consider the Boltzmann distribution of the molecules of reactants and product. Let's consider the A is going to convert into the B as a product and E is the reactant, right? So let's consider this reaction is exothermic reaction. We know that what is meant by exothermic reaction, right? Exothermic reaction. Now, when it is the exothermic reaction, if I write the energy levels of the reactant molecules as well as product molecule, that is called as the Boltzmann distribution. The energy level, we know that from the kinetic theory of the gases, we learn that some of the molecules have higher energy, some of the molecules have lower in energy. Population and this side energy, right? So if I write the energy levels of A, let's consider these are the energy levels of A, and this side let's consider the energy levels of B. I'll write in the different way. Energy levels of B. So these are the energy levels of B, and these are this dotted line. Dotted lines are the energy levels of A, and these red color lines are the energy levels of B. The Boltzmann distribution, if I write the Boltzmann distribution, this is the Boltzmann distribution. Right, this is the Boltzmann distribution. Again, I will write another diagram this side. Population, energy, the black colored lines are the energy levels of A, and the green color lines are energy levels of B. Again, this is the Boltzmann distribution, right? So what this indicate that when the reaction is in the exothermic condition means exothermic reaction means the energy is evolved, that is heat is evolved, right? When this heat is evolved, the Boltzmann distribution of the species A and B, these energy levels, Boltzmann distribution, right? The Boltzmann distribution of these energy levels, species B, A and B, it can be seen that reactant and product have the similar densities of the energy level. Similar densities of the energy levels means what? The spacing between this energy level, this energy level and 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 this energy level. What are these energy level? Kinetic theory of the gases. In the kinetic theory of the gases, we have learned that the different in the if I take the 1 mole of the substance, in that 1 mole of the substance, the molecules may have different energy levels. Some of the molecules have lower energy levels, some of the molecules have higher energy levels, like that. So there is difference in the energy level, right? So there is difference in the energy level. In this case, the energy levels of the species A and species B, this energy level, I can say that this is delta E and this is delta E. The energy levels of species A and B, the difference in the energy levels of species A and B are nearly same. Since it is the exothermic reaction, here the product B is predominant. Product is B is predominant, and it is expected that exothermic reaction will have the equilibrium composition that favors the product formation. Right? Now, we know that, but we know that the delta G is equal to, we have learned this equation, delta G is equal to minus RT ln K. Right? RT ln K. Delta G is equal to minus RT ln K. Delta G0, we can write delta G0 is equal to minus RT ln K if it is the standard Gibbs free energy. Right? This equation contains the delta G0, hence it is obvious that entropy plays the major role. How the entropy plays the major role? Because we have learned another equation, that is delta G0 is equal to delta S0 minus T delta S0, where delta S0 is the standard enthalpy, right? Standard enthalpy of formation. T is the temperature and delta S0 is the standard entropy of formation or standard entropy, right? So when the energy levels are less spaced means in this and this, right? If the energy levels of A species are less space means the energy levels are the gap between two energy levels of the molecule, that is reactant molecule, is very less. In that case, entropy plays the major role. Entropy plays the major role, and even though the reaction is exothermic, but when the equilibrium is attained, in that case, the reactant that is more favored. At the equilibrium, the reactant that is more favored means the B that is formed is again decomposing to the A. How it is possible? Because we know that if I rearrange this equation, that is this equation, if I rearrange that equation, that is ln K is equal to delta G0 minus RT. That is equal to ln K is equal to minus delta G0 divided by RT. Right? If I combine this equation in this equation and compare this equation, let's consider this is equation number 1 and this is equation number 2 and this is equation number 3. If I compare this equation and this equation, how one can write? That is ln K is equal to delta G0 that is equal to delta H0 minus delta H0 divided by RT plus delta S0 divided by R. How? Since delta H0 divided by RT divided by RT, since it is the minus sign, delta G0 is the minus sign, it will be become equal to plus, and this T will get cancelled. T will get cancelled. Therefore, instead of delta G0, we are writing lnk, right? Lnk divided by RT, right? Delta G0 lnk divided by RT. Similar way, we are writing that is delta G0 is equal to lnk divided by RT. Lnk, that this side, therefore it comes out to be divided by RT. Therefore, one can write this, that is, if I take the logarithm of anti-logarithm of this, k is equal to e raised to, this term will be in the power of e raised to minus delta h0 divided by RT, and again into e raised to, since plus according to the rule of exponential, if it is plus, it will be dot. E raised to dot means it will be product. So e raised to delta S0 divided by R. Therefore, for exothermic reaction, delta H is negative. For exothermic reaction, delta H is negative. Hence, K will be higher. It can be expected to have the equilibrium constant that favor the product formation as seen in this figure. But in the exothermic reaction, if the entropy of the reaction delta H, delta S is positive, then the equilibrium composition may favor to the reactant formation. That is, the equilibrium condition of the reaction mixture will move toward the product side, more product side. When it is possible, if the difference in the energy levels of the reacting molecule is very, very less, in that case entropy plays the important role. If the energy levels of the reactant as well as the product are in the same, means difference in the energy levels are same, in that case, if the exothermic reaction is there, in that case the more product will be formed, right? I hope you have understood this topic. If you don't understand, then watch it repeatedly. The next point is the response of equilibria to the condition. The response of equilibria to the conditions. Which conditions? On the once the reactant system has reached the equilibrium, we know that if A is reacting to the B and B is reacting to again forming the product, if the equilibrium is attained, that we write the K equilibrium. If this reaction mixture is in the equilibrium condition, then the equilibrium will be changed when we disturb by this equilibrium of the reaction. How one can disturb this equilibrium of the reaction? By changing the composition. By changing the composition, E means concentration. If I increase the concentration, the equilibrium constant will be shifted, right? If I decrease the concentration, the equilibrium constant will be affected. If I change the temperature or if I change the pressure, then and then only the value of this equilibrium constant will be changed. That is called as the Le Chatelier's principle. Remember that? What is Le Chatelier's principle? If the reaction is in the equilibrium, the reaction will be in the equilibrium condition unless and until we disturb that reaction. How we disturb that reaction? We can change the temperature, we can change the pressure, or we can change the concentration. If we change the pressure if we change the temperature or concentration, it will take the time to attain the new equilibrium. That new equilibrium, for the formation of the new equilibrium, that is called as that is according to the Le Chatelier's principle. So there are three types of the disturbance of the equilibrium of the reaction. We can disturb the equilibrium constant of the reaction. Number one is the change in concentration. Right? Number two, change in pressure or volume. change in pressure or volume. If the reaction is in the gaseous state. Number 3, change in temperature. Change in temperature. We will discuss these points in the next lecture. Right? Till then, enjoy the lecture. Bye bye.